In this problem, we would like to find the volume of the region between two paraboloids, z equals 27 minus x squared minus y squared, and z equals 2x squared plus 2y squared. So the first paraboloid opens down, and the second paraboloid is a little bit narrower and opens up. And to make it look three-dimensional, we'll do that. So we're looking for the region here encased by the two paraboloids. So in one variable calculus, if you have two curves, y equals f of x and y equals g of x, you want the area between them, then you would do the integral of the difference, the top curve minus the bottom curve. So if you want the volume between two surfaces, you'll do the double integral of the top surface minus the bottom surface. So in this particular situation, we have the top surface is the paraboloid z equals 27 minus x squared minus y squared, and the bottom one is z equals 2x squared plus 2y squared. And we can simplify that. 27 minus 3x squared minus 3y squared. So this is our integrand. Now the variables x and y vary over a region in the xy plane. So if we take a top view of this, then we will see a disk. You can see the disk I tried to draw here. Right there, that's a disk. So looking down on it from the top, it looks like this. So we need to know the radius of that disk. But clearly we would like to do a polar coordinate transformation here, and the theta goes from 0 to 2 pi. The radius will go from 0 to whatever that radius is. And the integrand is 27 minus 3r squared, because x squared plus y squared is r squared. So this is 3r squared if you factor out the minus. And dA in polar coordinates is r dr d theta. So let's figure out what this r is by just finding the intersection of these two surfaces. So we'll set 27 minus x squared minus y squared equal to 2x squared plus 2y squared, and we should get the equation of a circle. This is 27 equals 3x squared plus 3y squared. So 9 is x squared plus y squared. That's a circle of radius 3. So our radius goes from 0 to 3. Okay, there's no theta at all in this integral. So in this integrand, so the integral from 0 to 2 pi d theta is 2 pi. And then we have integral from 0 to 3 of, distribute the r, 27r minus 3r cubed dr. So that's our integral. One variable, polynomial, pretty basic. Setting it up is the real challenge. Now the antiderivative is 27r squared over 2 minus 3r to the 4th over 4. And we want to plug in 0 and 3. When we plug in 0 for r, we'll get 0. So the answer is 27 times 9 divided by 2 minus 3 times 3 to the 4th divided by 4. So we just have to work out the arithmetic. So this is 2 pi times 2 times 27 times 9 minus 3 times 3 to the 4th all over 4. So common denominator is 4. I just multiplied the first fraction by 2 over 2. And the number on the top here, we get pi, and we get 2 over 4, so we get pi over 2 times the number in the numerator. And the number in the numerator, this is 3 to the 5th, and this is 3 to the 5th. So we have 2 times 3 to the 5th minus 3 to the 5th, which is just 3 to the 5th. And 3 to the 4th is 81. So 3 to the 5th is 81 times 3. And that's 243. So 243 pi over 2 is the value of the volume between the two paraboloids. Again, the two paraboloids intersected in a circle, and that circle had a radius of 3. And so in polar coordinates, the theta is going to go from 0 to 2 pi, and the r is going to go from 0 to 3. And you can see the equations of the paraboloids makes it clear that we're interested in polar coordinates, because the first one is z minus r squared, and the second one is z equals 2r squared. So polar coordinates were very convenient.